Hello, today we're going to talk about how electrical currents produce magnetic fields. We saw in a previous lesson that magnetic fields can exert forces on moving charged particles, and similarly, conversely, I guess, moving charged particles actually produce magnetic fields. On this slide I have a summary of the qualitative side of this, which is that if get my little pointer out. So in this first picture here, the idea is that the current is moving in the direction of my thumb through that wire that I'm holding, and I have my fingers wrapped around the wire, and the direction of the magnetic field produced by that current matches the direction that my fingers are wrapping around the wire, like that. So I have that illustrated in a few different ways above. This wire, again, has the current going to the up, going to the top, going up. And so I've drawn the magnetic field lines sort of circulating around the wire in that particular direction. Unlike electric fields, remember that magnetic fields always have to form a closed loop. They don't have like a starting and ending point. And when it comes to just a single straight wire, like in that picture, the field lines are actually circular. They're perfectly circular. I've only drawn like one layer of circles, but it actually would be like many concentric circles of different radii. And the field gets weaker as you move further away from the wire, so the lines get further apart as you move away from the wire. I'm just trying to illustrate the direction there, not the complete field. Next to that, I have like a square wire loop carrying a current, and the current is going clockwise or counterclockwise. And on each segment of that loop, I've used the same right-hand rule. So along the top segment, my hand is like reversed in the camera view. But like on the top segment, if you have your thumb pointing to the left, and imagine holding that wire in your hand, you'll see that your fingers are going like into the screen above the wire, and when they wrap around, they'll be coming out of the screen below the wire. And so I've illustrated that with the traditional X's and dots. And you can use the same rule on the other edges of the wire loop, and you'll find that in this case, you always get dots on the interior and you always get X's on the exterior. If the current were going clockwise instead, that would be reversed. But it's always going to be the case for any current loop that the direction of the field on the interior is fixed, and the direction on the exterior is the opposite of that. And it just depends on whether it's like clockwise or counterclockwise, basically. The same rule is being applied in the other two pictures, but there, instead of the current flowing in the plane of the screen, the current is coming either out of the screen, which is the dot, or going into the screen, which is the X. And again, that's a convention that I discussed in a previous video. And so, again, to determine the direction of those circular field lines, just let your thumb be the direction of the current, whichever way that needs to be, and the sense of your pointing fingers tells you which way the field lines go. So that's the qualitative side, and many questions that the College Board asks about this, that's all you need to do. They ask a lot of conceptual questions about directions of the field, and so you need to be able to do this right-hand rule thing. There is a more mathematical side of it, which is on this next slide. This formula is somewhat scary looking, and chances are good that you won't have to actually use it because there is a better way of calculating magnetic fields known as Ampere's law. This is kind of analogous to the way when we started electric fields, we were using like the kq over r squared thing and had to do a lot of integrals. And then later on we learned Gauss's law, and Gauss's law was way easier for most situations. Same kind of thing is going on here. So this law is the fundamental relationship, and you can see that it even has some similarities to, say, Coulomb's law. There's like an r squared in the bottom. The source of the field is the current instead of a charge, but that's in the numerator. But let's talk about the parts here. So there's constants in the front, mu naught over 4 pi. Mu naught is the universe's fundamental magnetic constant. The name of it is the permeability of free space, which probably reminds you of the permittivity of free space, which was the electric constant. Similar to the electric constant, the free space or vacuum value has that subscript 0, and if you're doing a problem that does not take place in a vacuum, then you would use an appropriate value for whatever that medium is. The value is 4 pi times 10 to the negative 7th. There's nothing like mystical or amazing about the fact that it's exactly 4 pi times 10 to the negative 7th. That is just kind of a consequence of the way we defined a bunch of our units. The 4 pi is related to, excuse me, the 4 pi is related to spherical surface areas, just like the 4 pi's that you've seen in lots of other formulas recently. Okay, so there's also an I for the current. There's this weird cross product, which I'll talk about in a second. And then in the bottom, there's a 1 over r squared, because that's the way all these things work. So in the illustration on the left, I've drawn a sort of arbitrary curvy current flowing through space, because I want to emphasize that this law works for anything. It doesn't have to be just for straight line currents. And I've taken that current, I've selected a small little piece of the current, which I've labeled ds. So it's an infinitesimal section of the path along which the current is flowing. I want to calculate the magnetic field at this point P, that's off to the side. And the r vector goes from the source of the field, which is the little ds piece, and points from there to the point P, where I want to measure the field. I've also indicated a unit vector that points in the same direction as r. Unit vectors always have a hat instead of a arrow. And that r hat unit vector is what you see in the formula over on the right. Again, a unit vector just has a magnitude of 1. So in this cross product, it's being used solely to help determine the direction of the small piece of magnetic field that's produced by this small piece of the current. So if you want to know that direction, again, there's a cross product there. It says ds cross r. So the right-hand rule that we use for cross products, which I think has not come up since we were doing rotation, so like with torques and stuff, but you start by, the way that I teach it at least, start by pointing your entire hand in the direction of the first vector in the product, and then you need to bend your fingers at the first knuckle so that they end up pointing in the direction of the second vector. And after you've done that, then your thumb tells you the direction of the result. So the result is going to be perpendicular to both of those two vectors. If that's the first vector and that's the second one, my thumb points perpendicular to that. Now, in order to get your fingers to bend in the right direction, you're probably going to have to twist your wrist around until you find the right way to hold your wrist so that you can actually bend your fingers that direction. But that's the idea. So if you start with your hand in the direction of the ds vector and you want to bend them to be parallel to the r or r hat vector, you'll find that your thumb needs to be pointing into the screen in this case. And that's why I've indicated the dB vector with a little x to show that it's going inward. If you perform that same cross product for any other section of this current, you're going to get the same result. So like if I had a little ds that was here and the r vector went like this, you can even test that out with your right-hand rule, and you'll find that the direction of the cross product result is still into the screen. If I were to test a point P that's over on the other side of the wire, like over here, then I would be getting results that come out of the screen for the cross product instead. But as long as I'm on the same side of the wire, every piece of the current is going to give me the same direction. The other thing to note here is that the law is written in terms of a dB instead of like a total B. And that's because to find the total magnetic field at point P, I have to consider every piece of the current. And so you have to do an integral in order to actually find B for any current. You can't find the field of a current without doing an integral. So I'm going to show you a couple examples of this. I'm going to do them pretty quick. And again, it's unlikely that you'll have to actually do this on the AP exam. It does occasionally come up, but not a lot because, again, they prefer testing Ampere's law, which is a different method of finding these fields. And I didn't actually say the name yet, I think. This is the name of the law. Both of those names are French, so this is like Biot-Savart or something like that. Okay, first example. I have a circular arc that's carrying current upward, and I want to find the magnetic field at the center of curvature of that arc. So I place my point P at the center, through the arc. I'm calling the angular size or the angular extent of the arc phi, and I want to find B produced by that current. You might wonder, where is this current coming from and where is it going? And let's say a wizard did it. It doesn't really matter. Sometimes when they set up a problem like this, they'll say that that the rest of the circuit is outside of the plane of the paper. So like if the current at the bottom is coming from something inside the screen, it comes towards the screen and then turns into the plane and then goes away again. That would mean that they don't contribute to the field at P because of the cross products. But basically, don't worry about it. So if I want to know the total field B at that point, I need to add up all of the little dB contributions from every piece of the arc. I know that each individual dB is based on the Biot-Savart law. So I have written in a bunch of that. You can see the constants there. You can see the I over R squared. You might wonder why I wrote just a ds instead of like ds cross r hat. That's because I already know the directions are fine, basically, and so I'm not worrying about the cross product. R hat itself is a magnitude of 1, so I don't need to write it. And the direction, if you do your right-hand rule for the current down there in that arc, you'll find that the direction of the field at that point, I'll go ahead and draw this in. Actually, I'll do it in blue because I've been using blue for my magnetic fields. The magnetic field there is going to be coming out of the page, and that's just based on the right-hand rule. Because it's a circular arc, the R vector that goes from each individual piece of the current ds to my point P, it's always perpendicular to the ds. Like if you imagine this little piece of the path ds, the R vector has to point towards the center of the arc. Because it's a circle, those are going to be perpendicular to each other. So basically the cross product becomes trivial. So that's why I didn't bother with it. Okay, so I'm supposed to integrate ds over the entire arc. Notice that all of these things in my little neon box are constant with respect to my position on the arc. So I can just take all of that outside of the integral. The way I wrote it here is I rewrote ds as r times d theta, and then I'm going to integrate theta from 0 to phi. But the r also is independent of theta, so that comes out. And so I'm basically just integrating d theta from 0 to phi. And the result is this. So unsurprisingly, it depends on how much current, depends on the size of the arc, and this works up through a full circle, 2 pi. And it depends on the radius, because the bigger the radius is, the further away the current is from the field point that you're trying to calculate. So that's a pretty straightforward example for the Biot-Savart law, and that is something that it wouldn't be like crazy for them to ask you to do that, especially because so many aspects of it become trivial due to the setup, like the perpendicular vectors and stuff. A more difficult example is if you have a straight wire. This is a problem that they might ask you to like set up, but evaluating the integral is involves methods that they don't expect you to do during the exam, so they wouldn't ask you to evaluate it. Plus, if you need the result, you can get the result from Ampere's law in like 2 seconds, just like you can get a bunch of electric field results from Gauss's law in just a few seconds. So there's really no reason to do this other than to demonstrate that you know how to set it up, which they have asked. I have seen that asked, but it's not common. So anyway, I have this straight wire. I want to measure the field at point P, which is the distance big R away from the wire. I have drawn an arbitrary piece of the current ds. I've drawn in the r vector that goes between them. I've named this angle theta, and off to the side I've made note of a couple of things I'm going to need later, one of which is that sine theta is big R over little r. That's from SOHCAHTOA, opposite over a hypotenuse. And then the magnitude of the little r vector is square root of x squared plus big R squared. So first I write the Biot-Savart law. This time the cross product is meaningful because depending on which piece of the wire I'm looking at, that angle theta is going to be different, the angle between the ds and the r vectors. So you can see on the next line that I have a sine theta to take care of that part of the cross product. And that's the only like dramatic change that I made. I rewrote ds as dx because I'm just saying this is the x direction. And I put some absolute value on there because I can tell what the direction is going to be from the right-hand rule, as always. In this case, the direction of the magnetic field is going to be into the screen. So on the next line, I replaced the sine theta with big R over little r, like I wrote above. So now I have an r cubed down there. And then I replaced little r with the little r expression from above. And again, all of that is for dB. That is the tiny contribution to the total magnetic field of the tiny little piece ds that I've already marked. If I want to know the total magnetic field, I have to integrate all of those dBs for the entire wire. And so that's going to look like an integral from negative infinity to infinity of the expression that I got at the bottom of the first column. And again, evaluating that integral is not something that they're testing for. So they would have you stop here if they asked you to do this. the result is down there. And we'll be making use of that in some problems over the next day or two. But the better way to get that expression is Ampere's law, which we'll talk about later. Okay. One other thing I want to mention is that we now have a tool for determining how much magnetic field is produced by a particular current. And we already know that if a current flows through a magnetic field, it feels a force from the magnetic field. So what this means is that if you've got two or more wires that are carrying currents, they all produce their own magnetic fields, and that means that they're all carrying current through the magnetic fields that were made by the other wires. So I have an illustration of that here. I've got a blue wire making a blue field, a red wire making a red field. But clearly the blue wire is taking a current through that red field, which means the red field should exert a force on the blue wire, and vice versa. If we do some right-hand rule stuff for this situation where I've drawn both of the currents moving in the same direction, you can find that the wires attract each other. So if I think about the red current, for example, the red current is going up. You should follow along with your own right hand. That's facing the correct direction. But I know the current is moving up, and the field that the red current is flowing through goes into the screen, because the blue field on the right of the blue wire, where the red wire is, the blue field goes into the screen over there. So I've got the current going up, the field goes into the screen, and my thumb points to the left toward the blue wire. So the force on the red wire points to the left. If you go through the same process for the blue wire flowing through the red field, you'll find that that force points to the right. And that shouldn't really be surprising because this is an interaction between the two wires, and so their forces have to be opposites of each other. Same magnitude, opposite direction. If one of the wires were facing the other way so that the currents went in opposite directions, then they would repel each other instead. And if you want to know the magnitude of that force, I know that the magnitude of the force on a current carrying wire that's flowing through a magnetic field is ILB, assuming that the field and the current are perpendicular. In this case, they are. So if you want to know the magnitude of the force between the two wires, all you have to do is replace that B with the field of a wire formula that I just derived. I skipped the hard part, but that's the formula that I just derived for the field of a wire. So I've got like current 1, the length of the wires, and then the magnetic field produced by current 2. And you just lump them together. So you can write it this way, which has kind of a familiar, like with the I1, I2 on top, that feels a lot like Coulomb's law for electrical forces. Notice that it's over R instead of over R squared, and that's because you get 1 over R squareds for things that have spherical symmetry, like point charges, and you get 1 over R's for things that have a cylindrical symmetry instead. When we found the electric field due to a line of charges, for example, it had a 1 over R for the same reason. And I've also written it in this funny way where I divided both sides by L to put the L over on the left. That's referred to as the force per length or force per unit length on the wires. And the reason that I've done that is that sometimes physics questions are written in terms of the force per unit length, especially if they don't feel like telling you how long the wires are, like if they have an unknown length, or especially if they have an infinite length. You wouldn't want to use the first formula because you'd have to be plugging in infinity in for L, and that tells you the force is infinite. That doesn't really help. So the force per length is a little bit more usable in some ways. And so you may see questions that talk about it that way. And that is it for this particular video. The next topic is, I think, Ampere's Law. Yeah, this topic is Ampere's Law. And that will be the end of magnetism unit. But we'll get to that another day.